Okay, let's say one last thing, and this will probably not be so surprising, but when you take a function of three variables, then when you want to talk about partial derivatives, well, and let's go back to first partial derivatives, there's going to be not two of them now, but three of them, right? So let's say you have a w equals f of x comma y comma z. There's a partial derivative with respect to x. Kind of looks the way you'd expect to, right? So y and z remain the same. They are treated constant. And f sub y, f sub z, they're defined exactly how you'd expect. The point is to find the partial derivative of f with respect to x, treat y and z like constants. In other words, one variable will be treated like a variable, all of the other variables will be treated like constants. Okay, so let's try that. Let's take a look at f of x comma y comma z equals x times sine of y to the fourth plus 3z to the sixth plus x to the sixth yz and find all three partial derivatives. So first, with respect to x, we need to treat y and z like constants. So if y and z are constants, then sine of all this mess is a constant, right? So that's just a number written right next to x. So we just copy that number. As strange as it looks, sine of y to the fourth plus 3z to the sixth is, for the moment, being treated like a constant. So it's just like, how do you differentiate 5x? You get 5 for the same reason we write this whole sine thingy. And then y and z are constant, so we copy them down and differentiate x to the sixth as 6x to the fifth. Great. That's f sub x. Now we need f sub y, so go back to the original function. Treat x like it is a constant, and treat z like a constant for that matter. And when you differentiate now, you with respect to y, the thing to note is x in front of the sign, that's a constant, it's a coefficient to just copy in front. Apply the chain rule, yeah? So cosine of what's on the inside, and then you need to differentiate what's on the inside. Well, 3z to the sixth, that part differentiates to 0. The key thing is y to the fourth is, since y is the variable, I mean, so z is a constant. That's why 3z to the sixth is going to differentiate to 0. Y to the fourth is going to differentiate to 4y to the third. And then in 6x to the fifth z times y, all that stuff that I just said before times y, that should get copied. Oh, I'm looking at the wrong line. I'm looking at the f sub x line. I should look up at the top. Excuse me. So in x to the sixth z times y, all that stuff before the times y, which is x to the sixth z, that needs to be copied down. And then here's the partial derivative with respect to z. For the first term, very similar things as earlier. It's just because of now the chain rule, a different factor is going to pop out here, right? Because y should be treated like a constant, so y to the fourth differentiates to 0, but 3z to the sixth should differentiate to 18z to the fifth. And then finally, I'm looking at the right place now, up at the top, x to the sixth y times z, that derivative, treating x and y like constants, just should be x to the sixth y. Okay, so I hope that example makes sense. And then, you know, not so surprising, there should be a gradient. This should be a vector function. Just like earlier, it's just, earlier we got a 2D vector. Now you've got a function with three input variables, so there should be three components. You get a 3D vector. So this shouldn't all be too surprising. Here's now, let's find the gradient of a given function. And well, let's just first get the partial derivatives individually. And let me maybe not spell these out all. You can look through these carefully if you'd like to. I hope everything looks correct. I hope there's no errors. But the point is, all of these partial derivatives, there are three of them. They should just be stuck together with comma separating and angle brackets, and there's your gradient.